I'm going to begin recording, and let me see. All right, let me share my screen. Okay, and good morning and happy Friday to you all. I know sometimes it's easy to lose track of what day we are in the week, but maybe having school helps us remember. This morning, unrelated to coronavirus, this music legend Bill Withers had passed away, and I'm not sure if you guys are familiar with the music of Bill Withers, but I'm going to post a link in the chat. This one is Lovely Day. Yes, Lean on Me is another excellent song, and so maybe your homework just this weekend is maybe I'll post this link also to CCLE, but listen to a few songs by Bill Withers. Yeah, I just posted a link to Lovely Day, which yeah, you guys are sharing some great songs there. I think Lovely Day especially is just kind of a song that can brighten the mood. A lot of his songs, so great. And so I want you guys to listen to his music there. I would play the music over the Zoom thing, but I think if I do that, my video will get a copyright strike on YouTube when I post it to share, and then also I think the audio quality for music over Zoom just is not going to hold up there. But yeah, we'll get started, and so today we are going to wrap up what we started on Wednesday, which was working through ordinary least squares regression via matrix notation. Okay, and then we'll start taking a look at cross validation. And so where we left off on Wednesday, we were talking about taking the finding the gradient of a function where the input is a vector. Okay, so this is very similar to taking the derivative, and the reason for this is that when you want to find a local min or a local max for a univariate function, is that you would take the derivative of the function and you would set that derivative equal to 0 and you would solve, and that's how you can find a local min or local max. And it's very similar in higher dimensions, except instead of finding the derivative, you find the gradient. And so so we left off with this kind of table showing that if you got a function, all of these functions here, W transpose X, X transpose W, W transpose W, W transpose matrix CW, all of those functions will return a scalar, a 1-by-1 scalar value. And all of the and one thing to note is that when you find the gradient, okay, the gradient will always have the same dimensions as the input vector. So here, if our vector W is, say, has dimensions k by 1, if that is the vector that goes in, dimensions k by 1, and the output, the function outputs a 1-by-1 scalar, but the gradient coming in is k by 1, then the, if the vector has dimensions k by 1, then the gradient with respect to that vector will also be k by 1, okay? And so for W transpose X to be a 1-by-1 vector, if W is k by 1, W transpose is 1 by k, and X has to be k by 1. And so therefore, when you take the gradient of F with respect to W, it will have the same dimensions. So if W has dimensions k by 1, then X will also have dimensions k by 1. Okay. And so this is where we've left off, and this is the next step that we are going to do. So in the last lecture, we found the loss function in ordinary least squares regression. Our loss function is going to be the mean squared error. Okay, so basically the sum of squares residuals, but then divided by n. And we showed that if you use matrix notation, the sum of squares residuals, which we normally think of as y minus y hat quantity squared, okay, but in terms of in matrices, if we're using the t and the wx notation, then we can express the sum of squared residuals, or now the mean squared residuals, as this value, this product of matrix terms. There are no more summation signs. The summation is all handled in the matrix multiplication, right? And so here is our loss function. It returns a single scalar value, and it's 1 over n t transpose t minus 2 over n w transpose x transpose t plus 1 over n w transpose x w. So it's kind of a handful to say, but this is our loss function. And so what we are going to do is that we are going to find the gradient of the loss function with respect to w. So the gradient, so our vector w is a 2×1 vector, and so therefore the gradient of this loss function will also have dimensions 2×1, because that's kind of the rule of gradients, is that the gradient will have the same dimensions as the input vector. So here, the gradient, basically the derivative of L with respect to W, the gradient with respect to W is going to be a 2×1. So if I go through each term, how does this term t transpose t vary with respect to W? Okay, well, W is not in here, so it does not vary. Okay, so its gradient is going to be a 0 vector, right? And because we know it has to be the same dimensions, 2×1, it's going to be a 2×1 0 vector. So basically a 0 above a 0 in a vector here. Okay, here we have 2 over n w transpose x transpose t. How does this vary with respect to w? Okay, well, it's going to, following this relation, w transpose something, okay, well, it's going to vary basically x transpose t. This is how this term varies by this with respect to w. And we can check x transpose is 2×n, t is n×1, and so 2×n times n×1 will result in a 2×1 value. All right. And then over here, we've got w transpose x w. Okay. So this value here is very similar to this relation, w transpose c w. Okay. So it's almost, when you have a w and a w, it's almost like 2w, or w squared. Okay. So we've got w transpose c w. The gradient of that is going to be 2 times c times w. And so I've got 1 over n w transpose x w right here. And when I take the gradient of this final term with respect to w, we get 2 over n x transpose x w. Okay, so this, the w goes away, but we get a 2. And so this is what we have. We can check the dimension multiplication, and we will find that it is also a 2×1 vector. And so this is what we have. We got the 0 drops out, and now the gradient of L with respect to W is negative 2 over n x transpose t, that's 2×1, plus 2 over n x transpose x w. All right. I know this is a lot to start your morning off with. Okay, some of you might have just woken up 5 minutes ago or something. But here we've just done some, we've just taken the gradient of L with respect to W. Okay, so if this is good, give me a green check mark yes. Let me know that you're following along here. And if anything on this page has been too crazy, give me a red X, and we can kind of just take a moment to go over any terms in here that didn't quite make sense. Okay. Okay. All right, well, most of you guys are giving me green check marks. No one's giving me a red X yet. All right, okay, well, if you guys are feeling good, then so the next step, so we've found the gradient. So the next step that we're going to do is we are going to set this gradient equal to 0. I wrote the derivative, but I should say gradient. Set the gradient equal to 0. And then we're going to solve for W. We're going to set the gradient equal to 0 and solve for W. That's what we're going to do. All right, so here's our gradient. I'm going to set it equal to 0. Okay, and this is what I have. And here I can add multiply by 2 over n. I'm sorry, multiply by n over 2. Okay, and then add x transpose t to the other side. So I'm just rearranging some terms. I get x transpose t is equal to x transpose x w. And what I want to do is I want to solve for w by itself. Okay, and when you're doing matrices, there's no such thing as matrix division. Okay, you cannot divide by a matrix. What you can do is you can invert a matrix, and you can multiply by the inverse of a matrix. All right, so that is what we are going to do. We've got x transpose t is equal to x transpose xw, and in order to isolate this w vector by itself, I'm going to multiply both sides by x transpose x inverse. Okay. Now, when you do matrix multiplication, the order matters, and in this case, we are going to multiply the matrix that we multiply by goes in front of the term. So if when I multiply by x transpose x inverse, it's going to come to the front of here, and it's also going to come to the front here. And again, if you're not sure if it should have been x transpose t times x transpose x inverse, or if it should be, if it should be in this order, x transpose x inverse times x transpose t, you can always write the dimensions underneath these terms, right? And so when I multiply by x transpose x inverse, okay, x transpose x is a 2 by n and n by 2, which will give me a 2 by 2 matrix. The inverse of a 2 by 2 matrix is also a 2 by 2 matrix. And so I've got a 2 by 2 matrix, and here I've got x transpose, which is 2 by n, and t being n by 1. X transpose t is 2 by 1. And so the 2 by 2 matrix can only be multiplied by a 2 by 1 vector in the front. If I tried to do a 2 by 1 vector multiplied by the 2 by 2 matrix afterwards, this would result in a dimension mismatch. Okay, so it has to go in the front. X transpose X inverse, X transpose T. Okay, and so now I've got X transpose X inverse multiplied by X transpose X. So these two matrices, this 2 by 2 inverse matrix and this 2 by 2 X transpose X matrix, will cancel each other, leaving me with W on the right-hand side, and on the left-hand side, this entire thing is X transpose X inverse X transpose T. And when you match up all of the dimensions, this thing will have a dimension of 2 by 1, which makes absolute sense because W is a 2 by 1 matrix. And so therefore, the value of W that solves, sorry, let me mute my phone here. The value of W that solves or minimizes the minimizes the loss function, okay, that solves this thing where we've set the gradient equal to 0, is X transpose X inverse X transpose T. Have you guys seen this matrix form before for W? I don't know. Give me a little green check if you've seen that before, or at least if you're still following along with all of this here. Okay. Okay. So we're good. It looks like. Okay. And again, if anything I'm doing is doesn't make sense, feel free to raise your hand or give me a red X no, and that'll kind of indicate to me I need to explain something a little better. All right. Okay, so our ordinary least squares result here, okay, that is the estimate of W that minimizes the loss function of ordinary least squares regression, W hat, is X transpose X inverse X transpose T, okay? This is something that if you keep saying over and over, it it almost has its own little rhythm, and you can kind of remember it, right? So X transpose X, X transpose. I often say Y, but yeah, in this case it's T. X transpose X inverse X transpose T, or X transpose Y. So okay, so that is that, and let me just show you here how this could work. Okay, so here is the a very simple scatter plot of X. X is 1, 2, 3, 4, and T is 1, 3, 2, 4. Okay, so not a perfect straight line. We've got a little bit of, I guess, a little bit of scatter here, we might say. All right, and so so what is going to be the least squares regression line? Well, we can take X, bind a column of ones to it, and so I've got X, and here is the matrix X transpose times X. So X transpose X, when you take X transpose and multiply it by X, you're going to get this 2 by 2 matrix, 4, 10, 10, 30, okay? And then the inverse of this matrix, and perhaps you've forgotten how to find the inverse, so you know, review your linear algebra notes, okay? You know, you take, you know, the determinants and this and that. Okay, so this is going to be the inverse of this, all right? So this is X transpose X inverse, all right? And then, and what we're going to do is we want X transpose X inverse times X transpose times T. So here is X transpose X inverse. So the inverse function in R is solve. So you do solve, and you take the matrix X transpose times X. X transpose X inverse is this, times X transpose. And that produces a 2 by 4 matrix, or 2 by n. Well, we have to do matrix operations by hand. You might have to do a couple things by hand, all right? So you get, I expect you to be able to multiply some you know, small matrices, and at least take the inverse of a 2 by 2 matrix. I won't ask you to invert a 3 by 3 matrix or something. That's like way too much. But taking the inverse of a 2 by 2 matrix, I think, is a reasonable task that you should be able to do. Okay, and you might need to do some review there. Okay. And okay, so we've got X transpose X inverse times X transpose T, and that will produce this 2 by 1 matrix here, okay? And so this will correspond to the intercept being 0.5, and the slope 0.8, okay? So this is W hat, our estimated parameters for this, for the slope and intercept of a ordinary least squares regression line. In this case, is going to be X transpose X inverse times X transpose times T, and that is this 2 by 1 matrix, 0.5 and 0.8, okay? If I were to just fit a linear model using R, and I do give me a linear model where we predict T given X, okay, I get the same values. I get an intercept of 0.5 and a slope of 0.8, okay, which should be no surprise, because we just went through and we said this is going to be the OLS estimates, and indeed when we do linear LM and R, we get the OLS estimates. Okay, what do we do if we want predicted values? Okay, so if we want to see what the model predicts, we can take any input values X, whatever our input values X are. In this case, I'm going to just use the original values, and I'm going to multiply it by the fitted W, right? The fitted parameters are estimated parameters, W hat being the slope and intercept that we estimated, 0.5 and 0.8. And so if I take some input X and multiply it by W hat, these are going to be our predicted values. T hat predicts 1.3, 2.1, 2.9, 3.7. And I could plot those. I can plot the predicted values, W hat here, and this is exactly what I get, okay? Or I'm sorry, this is using the AB line, but yeah, these are the predicted values here. Okay. All right, so if I can do this for the Olympic data, all right? So the Olympic data, we have, you know, we're predicting the time based on the year the Olympics were held, again, how fast the gold medal time was for the 100-meter dash, okay? And so if I use LM, okay, use LM, it tells me that the intercept is 36.3, and for each year that has gone by, we're going to subtract off 0.013, okay? All right, now this doesn't, you know, that's like, if the Olympics were held in the year 0, 2,000 years ago, we would have predicted 36 seconds. You know, obviously that wouldn't have been the case to run 100 meters. But here we go, okay? And so, but we can still just say, well, let's try to fit using, you know, the operations we found, right? X transpose X inverse, X transpose T, and things like that, okay? And so I'm going to bind a column of 1s to X, okay? And so this is just kind of the head of first 6 rows of my X matrix. Okay, I've got 1s and then the year. And then we're going to just run X transpose X inverse, X transpose T, X transpose times the actual value is T. And what it says is we predict our intercept to be 36.309 and our slope to be negative 0.01327, okay, which is exactly what we have here, 36.309 and negative 0.01328. We can, 0.013275, so that rounds up to 0.1328. Okay, and so these coefficient estimates match exactly here. Okay, and again, with the predicted values, we can just take our input matrix X, multiply it by our fitted estimates of W hat, and we get some predicted values here. All right, and if we plot this, this will be the fitted linear, ordinary least squares linear regression line for the year, using year to predict time. So this is what we'll have. All right, okay, so from here, we can expand and get a non-linear response from a linear model. So in with least squares regression, okay, when we talk about linear regression, it doesn't necessarily mean that our predictions have to be exactly a straight line, okay? We can have terms, predictor terms, that are non-linear, and our response will be linear, except the relationship, when we talk about a linear model, we're just talking about the relationship between the output value y and the input value x is itself linear. So again, here's our Olympic data that we were just looking at. And here I'm going to expand my X matrix by adding a third column to it, okay? So before I had a column of 1s and I had a column of X's, and now I'm going to add a column of X squared values, okay? And so now we're gonna have basically polynomial regression, okay? And I'm just adding a column of X squared values. So X is now n by 3. I've got n rows and now 3 columns. Okay, and we can construct this matrix like this. I can take, I can bind the columns 1, okay, take X, and then I can square X, and 1896 squared is this big number, 1900 squared is this big number, 3,610,000. Okay, and so here I've got my X matrix will have n rows and 3 columns. Okay, so this is all I'm doing is I'm just adding a third column, which corresponds to X squared. Okay, and so our predicted value for a model that uses an intercept, an X, and an X squared value is going to just be the sum of W0 plus W1 times Xn. And now I've got another term here, W2 times Xn quantity squared, okay, Xn squared. So I got W2 Xn squared, okay? And again, I can represent this in matrix notation using W transpose X, okay? So I can say this product, if I say W is now a 3 by 1 column vector or column matrix, this quantity here is just W transpose X, W transpose X of n, okay? And that's exactly the same what we had for our linear model, right? So so again, I've adjusted my vector W, to be this column vector, column matrix, W0, W1, W2. This is your intercept, your slope in the linear term, and kind of your slope for the quadratic term, okay? Our predicted values is still going to be exactly the X matrix times W. The X matrix times W will give me exactly this, and that matches exactly what we want. Right? So we've got the X matrix times W. All right, so this term remains unchanged, and so my loss function is still exactly the same as it was before. My loss function is still going to be T minus XW transpose T minus XW, okay? So as far as what we did on Wednesday's lecture and what we have in today's lecture, these two terms are, this loss function is written the exact same way. The only thing that has changed, okay, maybe it's not the only, I mean, it's kind of a big change, but is that X is now, instead of having 2 columns, has 3 columns, okay? So on Wednesday, X was n by 2. You had a column of 1s and a column of X values. And today, now we have a column of 3 columns, column of 1s, column of X values, and a column for X squared, okay? But as far as writing the matrix, this is still just written as big X, okay? And so if we use matrix notation, we don't have to change anything, right? If we wrote kind of our predicted values here and we talked about what's the residual and we squared the residuals, you can see how this is going to be, now we have way more terms to expand, right? If we left it using kind of all 3 terms and we said that's, T minus W0 plus W1 xn plus W2 xn squared, and we expanded that out, it would be quite a pain. But in matrix notation, we're saving ourselves a lot of work, okay? And because the loss function is exactly the same in matrix notation, my fitted values, W hat, if you follow the exact same steps that I did, 10 minutes ago, you're gonna get the exact same results. X transpose X inverse, X transpose T, okay? We don't have to redo any kind of work here because we've done it in matrix notation. Okay, so by doing things in matrix notation, we've saved ourselves a lot of headache. Okay, if we didn't do it in matrix notation and we had partial derivatives, we would have to find the partial derivative with respect to W0, the partial derivative with respect to W1, the partial derivative with respect to W2, and solve for each of those partial derivatives to be equal to 0. But because we did our operations in vectors and matrices, we don't have to redo it. We can just leave it in the matrix form and get W hat to still be the same, X transpose X inverse X transpose T, which is why we prefer to work in matrices here. Okay, so this is a great thing. Okay, however, if you try and you say, okay, well, earlier I created my X matrix, okay, and I have a column of 1s, a column of X's, and a column for X squared, and you try to run that in R, and you say, okay, let's do X transpose X inverse, solve X transpose X inverse times X transpose times T, the actual values, you get an error. It says error in solve default this. System is computationally singular. Okay, and you're like, what does this mean? Okay, all right, so what happened? What happened is that R is not able to take the inverse of this matrix. When you do X transpose X, it is not able to take the inverse of this matrix. And the reason for that is because if you look at this column of values are very, very big values, right? We've got values on the order of 3 million, close 3 million, and when it gets to the year 2000, it's going to be a value of 4 million, okay? And so when you do X transpose X, okay, what you're doing is you're multiplying, basically taking that column of values So you're doing 4 million and eventually times another 4 million. And so that's going to be something on the order of a million times a million is a trillion. Okay, so you're getting something on the order of 16 trillion. And then you're going to sum this up for like basically 100, 28 different years or something like that. And so you get something on the order of 4 to the 10 to the 14th. Okay, this is a very, very big number when you take all of these things. Okay, and when you try to invert this, matrix with such big numbers, the computer chokes. The computer chokes because of floating point limitations, right? So the matrix does exist if we were using real numbers, but a computer can only represent numbers using 64 bits, right? And you got 52 bits for the mantissa, and so the smallest value it can represent is small, but this is reaching the limits of that the computer's ability here, right? So we're getting huge values on the order of 10 to the 14, and when you try to take the inverse, which involves multiplying by a constant, which is 1 over the determinant, okay, that value is going to be smaller than the computer's machine epsilon, right? So 2 to the negative 52 is on the order of 10 to the negative 16. We run into limitations of the computer's ability to compute these values. And so, so this causes what we call an underflow error in the computer. And it's because the computer is not able to represent, truly, truly, truly small values, which is some of the problems that we run into. So, so the computer declares that the matrix inverse doesn't exist. Okay, that's not true. The matrix inverse does exist. It's just we're not able to compute it when our numbers are this big. Okay, so one workaround is instead of using x squared as it is, you can just say, well, let's multiply x squared by a tiny value like 0.0001. Okay, 0.0001. Okay, and when we do that, this is what we get. Okay, so it's the same, basically the same thing as before, except instead of 3 million or something like that, now it's 361. Okay, so instead of 3,610,000, I get 361.000. Okay, all right, and so now now the computer will be able to do x transpose x inverse. Okay, so I called this thing where I've scaled this thing x scaled x underscore sc. Okay, and I'm able to do x transpose x inverse times x transpose times the observed values t. Okay, and here we get w hat. All right, and w hat looks like this. And again, if I all right, well, let me just pause here and just take a moment and just check in with you guys. Let me know if I've gone too fast or if this is all okay. Give me some feedback here. Okay, so you guys are okay, giving me a thumbs up here. Go slower, all right. And somebody has their hand raised. Charles, go ahead and ask your question. I'm trying to unmute you. Is that working?
Yeah. So when we scale it by like that 0.0001, we can use any arbitrary numbers, or is it just always
Yeah,
like
no,
that? Or
you can just use any arbitrary number, just so that you're not in the realm of having values on the order of 10 to the 14, where when you invert that, you're on, on the order of 10 to the negative 14, 10 to the negative, when you, machine epsilon on your computer is on the order of 10 to the negative 16, okay? And when you're doing calculations that will give you values that are smaller than 10 to the negative 16, right? So machine epsilon is kind of this relative term. I think I covered this heavily in 102A. It's this relative value, and when you get values that that go below that, the computer's not able to distinguish distinct values. Okay. So that's so it's just any kind of arbitrary value just to get things smaller. Okay. So I could have picked 0.001, that probably still have worked. I could have picked 0.00001, and that probably also would have worked.
So how come we don't have to change the other values?
You don't have to change the other value. I mean, these values are not causing problems here. Okay, Ivan asked, would the W hat and the X squared values have been the same if we didn't scale it? Okay, no, the W hats would change, okay? The predicted values would remain the same, but the W hats would change, okay? So for example, if you were to predict someone's, let's say someone's weight based on their height, okay? Now, if the height value was measured in inches, you would get one particular slope. You would say, we predict the person's weight in pounds to change for every change in inch, every additional inch. However, if you multiply every value of height by some factor like 2.54 to get centimeters, okay, the fitted predictions would be the same, but that slope value, that W value would change, okay? Because you're gonna say, you know, we predict the weight to change this much for every time we add 1 to the height in centimeters. So, so that's what would happen. So the W hat values would be different if you didn't use scaled values, okay? However, the prediction remains the same, okay? So even because, right, you've learned this in 101A, that correlation and basically your ability to make predictions doesn't depend on the unit being used. However, when you change units, of course, the slope is going to change because the size of the units have changed. Okay, and then yeah, Fan had the same question. All right, is that actually the formula for both cases? W hat is the same, and we just change our input matrix X. Yeah, for linear models. Okay. For linear models, W hat, ordinary least squares regression, will always be X transpose X inverse X transpose T. You guys are taking 100C right now, maybe? Okay, and if you do work in matrix operations, I think you'll come across this, X transpose X inverse X transpose T, and you'll find that that it's the same, okay? And so yes, your input matrix X changes, okay? We went from having 2 columns to 3 columns, and so our input matrix X has changed, but our estimates W hat remains the same. Okay, since the Rockford is asking, since the W parameters are different, do we need to multiply our observations by 0.001 before predicting? Okay, the answer is you don't have to yes, so what you need to do is you need to adjust your, the X matrix needs to match kind of basically the units that we're using here. So here we have, so you have you're plugging in your X, and you'd have to make your X squared, but then again, to make your predictions, you'd have to adjust that X squared column by multiplying by 0.0001, okay? Okay, Tanmay is asking, in a case like this, where our X values are just years, would it also work to just start counting from 1 instead of, say, 1896, so our squared values are smaller? Yes, that would also work. That would shift everything. And yeah, that's fine, okay? That would just be, so again, when you do linear regression, adding a constant to your predictor values X will not have an impact on the predicted values, okay? But of course, you would have to make that adjustment for everything else. So these are all different options that could be done, okay? What I did here was just kind of one workaround where using the values directly, okay? Because a lot of times, I guess this was partly also to illustrate the limitations of your computer, okay? A lot of times we can think the computer can handle anything, and it's simply not true. When you have a matrix like this, and you do X transpose X, and you try to calculate the inverse, sometimes you run into this problem, right? And if you're not familiar too much with the inner workings of floating point arithmetic, this kind of error result might not make sense to you, and you might think, okay, I'm doing something wrong. You have not necessarily done something wrong. It's just the computer is unable to calculate the inverse of such a large number, such a large matrix. So this was one workaround, but yeah, other workarounds involve just subtracting off a thing. If I fit the linear model to my kind of scaled matrix, okay, so here are the coefficients. I'm going to keep moving on here, and we're going to run out of time here, but I get the same predicted values. I get the intercept on this and the first order term and the second order term. Those coefficients end up being the same as well. Okay, so no surprise there. Calculating the fitted values are done the same way. You have to take the matrix, kind of your adjusted matrix after I've scaled them, and I can multiply it by W hat, and I get my predicted values. If I used my original X matrix where I didn't scale any of the values, I didn't scale that third column, then of course my answers would be way off, and we would have problems. So here, of course, however you formatted the input X has to be how you format it to make predictions. And here is what the quadratic fit looks like, right? So, so when I fit it using a quadratic term, this is what it looks like. Another option, and I don't want to get hung up on this, okay, is that R has the ability to fit kind of polynomial fits, right? And so there's a function called poly, and this will produce basically scaled values of X. So it has turned all of our years, 1896 and stuff. It basically multiplies it by some kind of constant and recenters it. And then it also takes the X squared values and it kind of shifts things around as well. And one advantage of this is that poly will create uncorrelated values of X and X squared. Okay, so given the range that that you provide, it's going to produce uncorrelated values of X and X squared. Okay, and so this is an option, and basically the relationship between this column and this column of X squared values is that all of these values, you know, we've basically just subtracted a term and multiplied it by some kind of scaling value here, okay? And so you can fit the linear model to some polynomial here, which in our case is a second order polynomial. And we're gonna get this, and we can still produce the fitted values. And if I were to plot this, I would get the same fit, okay? So if we look at this, if we look at these fitted values, 11.3229 and 11.228, these are the same values that I got when I did it myself manually. Okay, so when I did it myself manually and I said fit the predicted values, I got 11.3229, 11.228, 11.136. Okay, and here I've used R's polynomial function, so I don't have to manually create my vector. I mean, not vector. I don't have to manually create my matrix of column of ones, column of x's, column of x squared values. And when I do that, I get this. Oh, yes, thank you. Have I given the quiz answers? No, I forgot to give the first quiz question. First quiz question will be A as in apple, and I might as well give the second quiz question answer. The second quiz question answer is B as in boy. So today it's A and B. A as in apple, B as in boy. Thank you for that reminder, Angela, to give you guys the quiz answers for the lecture today. And so we can see that using R's polynomial function back here produces the same fitted values. So these are the same fitted values that we got when we manually manually created our X matrix of column of ones, column of x's, column of x squared terms. Okay, and so this is going to be the quadratic polynomial, second degree polynomial fit there, right? So, and again, this is just kind of a handy function, so you don't have to go about manually creating, you know, your matrix of ones and x's and x squareds, and then scale them appropriately if you run into computational issues. Okay, using R's function poly takes care of all of that for you. Okay, so if you plan on fitting polynomial functions, we recommend using this rather than manually creating all of these things yourself. And we can see that we would get, despite all of our coefficient terms being different, we can see the predicted values are exactly the same as before. Okay? And so that was a second order polynomial. And so now we can just say, well, what if I fit a third order polynomial or a fourth or fifth or sixth order polynomial, all right? I can easily create all of these different order polynomial fits using R very quickly using this polynomial function, okay? So I don't have to go and create another X matrix where I'm taking column of ones, column of X's, X squareds, and now X cubes, and then X to the fourth power, X to the fifth power, X to the sixth power. Okay, I could do that. I could do that, and I would get the same fitted values. I could do X transpose X, inverse X transpose T. I could do all of those matrix operations, and we would get the same thing. Okay, but this is a quick way to fit different polynomials using R's poly function, which produces, this poly function produces matrices for us. When you use LM, it fits the intercept for us. And so here I'm fitting polynomial of degree 3, that's going to be model, polynomial of the 4th degree, polynomial of the 5th degree, so on and so forth, okay? All right, is this good with everybody? Good so far? Okay, and now I'm going to plot the fitted values for all of these things. And here we have this, I don't know, kind of pretty thing because I've got different colors going on here. And so this red line represents the linear fit, okay? Red is going to be the linear fit. And then orange is going to be quadratic. Green will be the third power, cubic. Blue, purple, and dark gray will be the different orders. So I've got linear, quadratic, cubic, to the 4th power, 5th, and 6th power. And we can see that they have different fits, all right? And so we are going to, I'm going to run out of time here, but the next question is, which of these polynomials or which of these models does the best job, right? How do you pick, out of these things, how do we pick which model does the best, okay? Which model should I use, okay? And so in your, well, you guys took 101A, so you tell me, what do we do? How do we pick, I guess I wrote the answer here. Okay, how do we pick which model that we should use? And the classical traditional approach is you look at the summary tables, right? So here's the summary table for the polynomial of 3rd degree, okay? And we can see, okay, we're looking at each coefficient and we can see, all right, the first order term is highly significant, the second order term is significant, the third order term is significant, so maybe a third order polynomial is good, okay? Other things you can look at, right? You can look at the AIC or the BIC, which has these penalty factors for having too many terms or having model complexity and stuff like that, right? What you don't want to do, you don't want to just look at your R² values, right? The R² value all by itself is always going to go up, always going to go up as you increase the number of terms. So, so if I look here, my R² value is 0.8973, and here is the 6th order polynomial, and my R² value goes up to 0.9233, right? So the R² value is always going to keep going up if you just add more terms. So that's not going to be a good way, right? Other things you can do is look at AIC, look at BIC, and that will give you some information, okay? Jonathan is asking, is there a way to choose the polynomial based on visually looking at the plot? Okay, maybe. It's kind of hard. It's kind of hard. You can look at it, and certainly our eyes are good, but there's a problem here, right? One of the issues is that we're fitting data to the observed values, okay? And there's we run the risk of overfitting, okay? And so I've run out of time. So on Monday, we're going to talk about choosing how to pick a model using this concept called cross-validation, okay? So I will cut all of these cross-validation slides and I'll move them into Monday's lecture for next week. But so this is where we're gonna leave off. We've fit several different models. Well, okay, so let me just kind of rewind. We did ordinary least squares and matrix notation, and we found that I hope the hope of this was that by using matrix notation, we've simplified a lot of our work, right? Using matrix notation feels kind of hard, but it also simplified a lot of work. We didn't have to find all of these different higher order terms, you know, partial derivative with respect to W0, partial derivative with respect to W1, partial derivative with respect to W2. We can have just used the same work using matrix notation. And then what we've done is we have now fit several polynomials of different degrees, and now we are faced with the problem of how do I pick which model is going to be the best. Okay, we will end here for today, and have a good weekend, you guys. Stay safe out there, and we will see you guys on Monday. So I'm going to go ahead and stop the recording. Where's my term here?